Good evening. Welcome to Krishna's class. We continue with our characterization of compact metric spaces. In fact, we have considered four statements, namely X is compact, X is totally bounded and complete. Every infinite subset of X has a cluster point. And the fourth statement is every sequence in X has a convergent subsequence. This is what is called the sequential compactness. Now, our strategy had been to prove this cyclically, namely, we prove 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 5. So that from which you can get the implication of any pair of them, or the equivalence of any pair of those statements. As usual, this is a standard procedure. What we have already proved is the first statement, that is X is compact, implies X is totally bounded and complete. That is the second statement. And we further proved if X is totally bounded and complete, then that implies every infinite subset of X has a cluster point. And this is where we stopped in our last lecture. Now, in this brief lecture, we now prove that the third statement implies the fourth statement. Namely, we assume every infinite set, that is, every infinite subset of X has a cluster point. Now, what we assert is that this implies 4. So, claim 4. That is, every sequence in X convergent subsequence. Tonight, this is what we want to take it up. Okay, this is quite easy to prove. So, what we do, we take an arbitrary sequence from X and show that it is a convergent subsequence. So, let's in X. Now, what we want to prove is that it has a convergent subsequence. Okay, now we observe that there are two possibilities of such a sequence. We'll take out this now. The two possibilities are the number of distinct elements in the sequence is finite. That is one possibility. The second possibility is that it is infinite. Okay. So we start with the first one, namely the number of. So there are two possibilities. The first one, the number of distinct elements of finite. So we take up this case first and then go to the second case. The second case is that the number of distinct elements of Xn are infinite. Okay. Okay. So let us take up this case first. Now we look at the sequence as a map. It's a fundamental definition of that is, we take X from X defined by Xn. Now, if the number of distinct elements of Xn is finite, now in case 1, what we have, the range of finite. Okay. So, you see, if you are having finitely many elements, with that you have constructed a sequence, which means one or many of these distinct elements have to be repeated infinitely many times. This implies one or many of this range. The range of X appears infinitely many times. So what is happening? If so, we can extract a subsequence from it, which is a constant sequence. Okay. So let us assume that X capital N is one such. Then we can construct a sequence, obtain a of xn consisting of now let us write it up. That is, there exists n1 etc. in the increasing order such that for k equal to 1 so that's a constant sequence that you have. Now this is a subsequence. Now this then sen which being a constant sequence converges to that is limit tending to infinity thus in this case you have a finite, a convergent subsequence. That means 4 holes. Okay, now we take up so we have not exhausted all the possibilities. The other possibilities are you may not have a situation like this, that one of them is repeated infinitely many times, or see that they are distinct. Now we consider is 2 where assume or the range of infinite. Now you see, thus the xn is an infinite subset of x. Therefore, 3 implies, we are assuming 3. So every infinite set has a cluster point. I will put it this way, xn is the image of this, because this is infinite, therefore it has a cluster form. Okay? Right. That is the range of let x denote or x tilde. What does it mean? X tilde is a cluster point means what? If you take an open neighborhood of any open neighborhood of x, the particular point x tilde, then it will contain infinitely many elements on the subsequence. Okay? So, right. Then what we can say is that there exists xn such that What you have done is you have taken the x tilde, you have taken the 1 by k neighborhood of that. This is the 1 by k neighborhood of that. That is, this is actually b x tilde 1 by k, right? Then there exists elements x and k such that this is less than. So we pick such element. So for each of these neighborhoods, for a fixed k, you have an x and k. Therefore, let us now take all these elements. So now choose xn such that the sequence nk is an increasing sequence. And that is possible. Then what we have is, we have d of as k tends to infinity. What does it mean? That is because you see that the distance between x and k and x tilde is less than 1 by k. So as k tends to infinity, that the radius shrinks to 0. Therefore, the sequence x and k or the subsequence x and k that we have extracted out converges to the point x tilde. Thus, the sequence, the subsequence see, this means that in both the cases, namely, if the range of this x map or the sequence xn is built up with finitely many distinct elements, you have a subsequence which converges. Therefore, the condition 4 holds. And in the case 2, there exists, we have extracted a subsequence from the given sequence which converges to the so-called accumulation point. Okay. So, in both the cases, that is, it takes care of all possibilities. Thus, 3 implies 3. Thus, that completes the proof. Okay, thank you very much. It's a very short lecture, just proving one part of our statements, namely P implies 4. Now, in tomorrow's lecture, we will take up 4 implies 1. Therefore, the cycle would be complete and we would have completed the characterization theorem. theorem proved. Okay, thank you very much.